opposing a Jew.
Well, good afternoon, everyone. Christmas Ben is my name, alongside John Casadubin Liger. The title of our project is Explainable Machine Learning Techniques for Predictive Crime and Health Monitoring. Um, sorry about that. Sorry about that. Let's proceed. Um, that is going to be our table of content or our points of focus today. We shall look at the introduction, the related works of our project, the problem statements that we try to cover or find out, the research questions and objectives, research contributions, methodology, system architecture, data description, and other that they follow. Then our brief introduction one, the tech advances in our project one, we had the sensors which are responsible for collecting data. We had the edge processing, which was to enable the real-time analysis of results that we gain via the sensor and then from historical data. Then the current challenges that we're trying to address, one, we have there was no real-time diagnostics of results since they were using cloud technology, which are which was covered up with an issue of latency. Then the traditional methods, which were also lacking the proactive fault detection. Otherwise, they were not efficient in predicting faults. Then the solutions, one for tracking engine health for predictive maintenance, then for real-time diagnostics, and then one we mainly focused on machine learning algorithms, which are to use sensor data and then historical data. And the benefits of our project, one are to reduce the unscheduled breakdowns, so as maybe to increase saving or to prevent frustration during someone's maybe away as they're going to work. Then two is improving vehicle reliability. Reliability make the focal, we can look at it in the sense of tolerance to failure. Then the potential impact is one, transforming the predictive maintenance. Yeah, as we feel this is a novel invention or innovation in this field, then ensuring optimal vehicle performance as well. Then one we involved sorry. Two, we have the predictive analysis systems such as deep learning, recurrent neural networks. All these take advantage of data generated from sensors coded onto the vehicles as well as the historical data, making predictive maintenance possible. These are some of the related works that have been established in line with our projects. Then we also have edge processing, which was to address the issue of latency that happened in cloud processing of diagnostics, employing machine learning models such as the support vector mechanism, the artificial neural networks, and concepts of ensemble learning, which make real-time diagnostics possible. Then here we are looking at the problem statements that we found, the computational problems that we found during our research works. One, they're telling us to predict breakdowns before they occur, we must address the latency issues and data failure issues. Now, this one was covered in the issues of edge processing using the sample learning models and then the posting models as well. Then to simplify training and improving model accuracy, we must navigate complex, noisy conditions that channels traditional physics models. And this was discussed in a paper titled Deep Learning in Mechanical System Signal Processing. Yeah, this is where this problem was found. And then to implement predictive maintenance for engine components, we must manage production costs and optimize sensor installation. Remember, these sensors are the one that will pick data. And then if they're expensive, meaning that the ability for us to keep track of all this information that is used to train the machine learning models is hard. So if they're made affordable, then yeah, it will ease up the process. Then to boost productivity and economic growth, we must eliminate vehicular irregularities that diminish vehicle confidence and waste time. Yeah, very well, so that if vehicles break down when you're not aware, they might affect your economic maybe let's say figure, whereby you have to face the unplanned repairs and maintenance and so on. Then the objectives of our project, one, developing machine learning models based on one, sorry, to develop a machine learning based predictive analysis system. In other words, we are to focus on using machine learning algorithms to build a system that can predict failures of the state of the car. Then to gather sensor data and apply feature engineering insights. Yeah, we very well saw the integration of IoTs in our project, whereby to gather data, then we use feature engineering to identify the specific feature or target items that we are to use. Then to accurately predict engine performance and detect anomalies. Then utilizing real-time engine diagnostics or identifying. Then to conduct proactive preventive maintenance as well. Mhm. Our dataset description, basically our dataset is having 1,100 entries with five variables which are listed down here, including the engine temperature, the brake pad thickness, and the tire pressure. Whereby some field, for example, the maintenance activities was consisting of categorical data, in other words, texts, which we went ahead uh, to encode to numerical data since we're dealing numerical data. Well, for now, let me stop it at that, and I invite my colleague to proceed.
It's Chunga Sajone, and I'm going to be taking you through the remaining part of our work. So I'll start with research contributions. These are what we have. Our work, we built costing models to enhance the performance of self-paced models. Then it also implemented ensemble learning to the support vector machine as well as artificial neural networks. And then KNN and KNN. Then we also suggested a novel solution for proactive maintenance and real-time diagnosis, hence predictive maintenance. So as it was before, people were predicting, but depending on values or depending on values of features that are coming from the cloud. Now here it's done in real time and there is no latency. We implemented a variety of models all based on car condition historical data, some of which is sensor data, to make decisions about the condition of the car. So this is the methodology. This is the visualization of our methodology. So the first thing was data acquisition, that is, we're able to look for a data set, then we pre-process the data, that is cleaning, scanning features, then handling categorical data, and we converted it into handling text data, and we converted it into numeric. Then we split the data, that is training, testing, and validation, whereby training was 70, testing was 20, and validation was 10. Then we built and trained the models. Then evaluating of the performance, that is where we carried out those are the accuracy, precision, recall. Then in case of NLO accuracy, we are able to do some hyperparameter tuning. And you can see it's a what? It's a loop. Then finally we deployed. Then these are some of our results. So the first table is showing some ensemble models. Then the second table is showing the deep learning models. That is deep Boltzmann's machine, deep Boltzmann's networks. Then the third table is showing models. Those are hosting models. So these are some of our explainable graphs, the vision matrix of one of our models. So you can see that in this explainability, the engine pressure, that is a feature in our data set, was contributing more, that was impacting more on the final label being outputted more than the other features. Then conclusively, the project develops the project that we did develops a car engine health monitoring system using various machine learning models. Then emphasizing data quality and feature engineering for accurate prediction, balancing model complexity and interpretability. So these are some of the limitations or the disadvantages. Extracting relevant features. Then there was a problem of handling categorical data. Then overfitting and maybe underfitting. We didn't include it there, but it was also a problem. Then integrating predictive model challenges, real-time interface on source limited onboard systems. So these are limitations and recommendations. So those of the limitation of extracting relevant features from raw data, we invest in advanced feature extraction techniques. Those are the ones that help us to extract the relevant features. Handling categorical data. When the system deals with numeric data, we implement a robust data preprocessing pipeline to help us convert the text data into numeric data. Then some models lack interpretability. So balance models complexity. You balance the model's complexity and interpretability. Then overfitting, we use cross-validation and diverse data sets to avoid overfitting. Integrating models into existing systems. So we collaborate with engineers for smooth integration. That is, we are collaborating with our mentor. Then this is our acknowledgement, and this is the end of our presentation. So thanks. Bye bye.